عليكم السلام ورحمة الله وبركاته. صباح النور.
Okay, so this is our second lecture in chapter 1. Okay, so last time we talked about degrees of freedom. Okay, and we say we have single degree of freedom and 2 degrees of freedom and so on until we get into infinite number of degrees of freedom for a continuous system. The type of the problems or systems we have here in single degree or 2 degrees, we call it discrete mass system, that the masses are lumped at points, okay, without any description of the shape or dimensions. Okay, so we call it discrete and or rigid bodies. Okay, so we have, by increasing masses, as you can see here, and springs, then we increase the degrees of freedom. So it's called discrete or lumped mass parameter system until we reach the continuous system. The continuous system, we have, what makes this is different than the systems above is that the mass here is distributed. So for continuous system, we have mass distributed system. Okay, distributed along the length of the beam. So we usually introduce a coordinate here, and then the mass is different at each point, or there is mass at each point, and which makes the system has infinite number of degrees of freedom. We will approximate in this course. We will only do discrete mass parameter system. So we will, in case we have beams, we will either assume that beams are massless or can be represented as approximated as a single degree of freedom system or discrete. Okay, so the importance of determining the number of degrees of freedom is to that will give us an idea how many frequencies involved in the system. Okay, here is this last page in this note. Okay, so this page is, or slide is about classification of vibration. Okay, here are listed some of the important classification. The first one is the free vibration. Okay, so definition of that is the free vibration takes place when a system oscillates under its own after initial disturbance. No external forces act on the system, and the system under free vibration will vibrate at one or more of its natural frequencies. Okay, so example of such vibration you can is the pendulum. Okay, or any spring mass system. A pendulum when it is supported vertically. Okay, so here we have this is the equilibrium line. So if the mass of the pendulum is not disturbed or the pendulum in general is not disturbed, then there will be no vibration. But you can give initial disturbance to start the vibration. So you can move this to an initial point with angle, let's say theta 0. Okay. So, and then you release. So you move it by your hand, for example, and then you release it. It's going to oscillate. So what makes this oscillate is the weight, okay, which is mg. There is change in potential energy, change in kinetic energy, and so on. So this keeps oscillating. If you assume there is no damping, this will keep oscillating between two extreme points. Okay, one and let's say 1 and 2. For no damped system. So there will be, first of all, no external forces here. Once you release from point 1, okay, no external forces are applied. And system still will oscillate. And in this case, when it oscillates, it will oscillate with a frequency. So you can see that at the beginning we give theta 0, and then it will keep oscillating. If you measure theta from the equilibrium line, okay, from the vertical axis, then theta is changing. So starting with, let's say theta 0, and it will go back this way, right? It will move this way until it reaches 0, right? Well, because we are measuring it from the equilibrium line, and then move to the next extreme point, okay, which will be again equal to theta 0. There is no damping, but in the negative part, right? So it is from plus to 0 to minus. And then it will go back to the equilibrium and then pass it to point 1. So it will oscillate. The oscillations occur at a frequency okay, there will be oscillations, and that oscillation will occur at a frequency called natural frequency. Okay, natural frequency, it means the frequency that is dependent on the parameters of the system, not on the dynamics part. Okay, so what will affect the frequency of oscillation is the length of the cord, right? So if you have a pendulum with this with the length cord of this much, or if you have a pendulum longer, then the frequency of oscillation will be not the same in the free vibration, because this is L1 and this is L2 and L2 greater than L1. Okay, and you can have another example like L3. Okay, so in each one, if you have the mass is the same, then the frequency, natural frequency, after releasing, disturbing and releasing, will be different depending on the length of L. For a given pendulum or any system, the natural frequency is constant, assuming it is constant. Okay, constant function of the parameters. Okay, function of the parameters of the system. Okay, what are the parameters of the system? We have for the pendulum, we have L and M. Those are the parameters. So the natural frequency, which is designated as omega n. Omega n is a function of L and M, might be M as well, but for sure it is L. As another example will be a spring mass system. If you have spring with mass M1 and K1. Okay, this system can be disturbed. This is the equilibrium line. So you can give an initial downward motion and then release. You remove your hand. Let's say you push with your hand M1 downward, so it will deflect to certain level, and then you can release. Remove your hand. Then it will keep oscillating about the equilibrium position. So omega n here is function of the parameters which are of the system, which are M1 and K1, function of M and K. Okay, so if you have M1 and K1, and then you have another system with M2 and K2, or you change one of the values, either the mass or the spring, then omega n will change. But it is not function of time. Omega n is not function of time. This is one of the assumptions, that omega n is not function of time. Now, what is definition of a frequency? Okay, we call this as natural frequency. If you go back to the pendulum, maybe easier to illustrate the frequency. If point 1 is the starting point, okay, so this will go from point 1 to point 2, which is the second extreme, and then back to point 1 is called cycle. So cycle is measured as or considered as the pendulum moves from extreme left, extreme right, which is point 1, to extreme left, which is point 2, okay, and back to point 1. Okay, this is one cycle. Okay, the time to cover one cycle is called period of oscillation. Okay, definition of okay, so time is for one cycle is called period of oscillation. And it is given as tau, measured in second. And anybody knows what is definition of frequency? Hertz. Okay.
Reverse دكتور.
Huh? Hertz. Okay. Right. Hertz is a unit, right? This is the unit of frequency. But the definition of frequency is F equal to 1 over tau, which is the reciprocal of the period of oscillation. Okay, given as cycles per second. Okay, cycles per second. And that is hertz. That's the definition of unit hertz. So the natural frequency, and we usually call it omega n, it is, or Fn. Okay, Fn is in hertz, omega n is in radian per second. Okay, one thing I also assumed that the natural frequency is constant, depends on the parameters of the system. For the pendulum, it is L and M. For the spring mass system, it is K and M. And then I define a frequency as the reciprocal of time of one cycle, which is not function of K or is not function of L. This is, you can use your stopwatch and measure the time for one cycle. Okay, and that will be time, but and that will not be constant because you can give initial distance, initial theta 0. Okay, different. You can give 5 degrees, you can give 10 degrees, right? So the time to take for 5 degrees is going to be less for 10 degrees, or you give 15 degrees. I'm just incrementing by 10, by 5, and so on. So how come we say it is a constant? This is an assumption that omega n for systems with small oscillations, okay, will be considered to be a constant. Okay, so we don't go up to more than 10 or more than 20 or take 90 degrees. For sure that time will be for a cycle is going to be different. So usually when we say that omega n or the natural frequency is constant, it means that we are referring to small oscillations. Okay, so it is constant provided that oscillations are small. We are talking about small oscillations. So 5 degrees or 10 degrees might be the same, you know, the time is almost the same. If you make a truncation to time, okay, let's say you can ignore the changes up to 2 decimal places. Okay, so if you take 5 degrees and then take 10 degrees, the time will be maybe will change after 2 decimal places. So you can make an approximation that the time are the same. Okay, so for large oscillations, this will be not true. That natural frequency is not just function of the system parameters. It will also be function of initial disturbance or initial conditions. So in general, but this is not what we will do, that natural frequency is function of the system parameters and initial conditions, to be more precise. But for when you make oscillations, but that will be very difficult to analyze. Huh? But when we limit the oscillations to small oscillations, we can say that the natural frequency is function of the system, of the parameters of the system only, not as function of the initial conditions. Okay, so that is one thing. You might always wonder why we say it is constant. Okay, the reason is we will only study small oscillations. Okay, and with small oscillation, that natural frequency can be assumed as function of the parameters of the system only. Okay, this frequency is when, if it is single degree of a freedom system, it is going to be 2 natural frequencies if the system is 2 degrees of a freedom, and so on. So the natural frequencies will be, the number of natural frequencies will equal to the number of degrees of freedom. So if you have a pendulum as shown here, this is called single degree of freedom because there is only one theta to describe the motion of the pendulum. But when you have a pendulum, 2 pendulums, okay, let's say we have this pendulum here and another pendulum, 2 joint pendulum with L1 M1 and L2 M2. Okay, this is called 2 degrees of freedom, and instead of having 1 natural frequencies, there will be 2 natural frequencies. Or if the spring mass system is made of 2 springs and 2 masses, okay, let's say K1 M1, K2 M2, then there will be 2 natural frequencies. This is 1 natural frequency here.
دكتور انت قاعد تكتب؟
ايه
دكتور انا ما يبين عندنا.
تشوفون الون نوت ولا لا؟
نشوفه بس للحين على تو مكتوب ان سكندز وللحين على المكان من قبله يعني.
مشير يعني. من عندكم الكل كذي لو بس عندك؟
المفروض الكل ما ادري يعني.
ممكن احد ثاني يفيدنا؟
انا نفس الشيء معك.
اكو تعدد
تو شوي
راح
طلع.
نشوف.
تو طلع.
اوكي. اوكي، فانا بعيد لكم اللي قلته. اوكي، يبين هني 2 بندلمز.
اي
اوكي، يعني قاعد اقول ان 2 pendulums, when you join 2 pendulums this way, then you will get 2 natural frequencies because this is 2 degrees of freedom system. 2 degrees of freedom system. Okay, and also this is this was 1 degree of freedom system with 1 natural frequency. This is also 2 degrees of freedom system. Then there will be 2 natural frequencies. Okay, the more the bigger is the number of degrees of freedom, it is more complicated to study, and we'll have more natural frequencies. So most of what we will do is about single degree of freedom, except in chapter 5, which is the last chapter. We will do more than 1 degrees of freedom. But this is the essential thing that you have to learn in this course, is the understand the theory of vibration of single degree freedom of different types of systems, damped and undamped, translation, rotational, and then we can build up on this knowledge to by the end of the semester to consider 2 degrees of freedom or more. Okay, now this natural frequency, in fact, is very important quantity. Okay, let's call it omega n. Okay, this is very important quantity in vibration. The second category is force vibration. Okay, force vibration takes place, here is definition, under the excitation of external forces. I told you the meaning of excitation of a force or force excitation. Force excitation, it means that the system is, there is a force exerted on the system with frequency. That becomes excitation. A force in one direction, like a dead weight, is not going to cause excitation. Okay, so excitation or force vibration will occur if a force is applied on the system that is changing because of frequency of excitation. Okay, there is frequency as well. So the force is applied with the frequency. Let me give you an example of how a force can change with the frequency. Okay, suppose we have a rotating disk, okay, supported. Here it is rotating, but this is supported on, okay, which has spring mass system. Okay, if this is rotating with omega angular speed, omega is angular speed. Okay, angular speed is also given in RPM, any revolution per minute, or given as radian per second. RPM means cycles per minute. Radian, it is it is multiplied by 2 pi. You know, you multiply this by 2 pi and divide by 60, you get radian per second. If the disk is balanced, then there is no vibration. But when the disk has a heavy spot, which means that the center of gravity is not the same as the center of geometry. Okay, there is center of gravity, which means the location of the weight, and there is center of geometry. If this geometry is circle, then it is the center is the center of geometry, the center of the circle. But if you have a mass added here, small mass, then you are shifting the center of gravity, right? And this, when in rotation, will give a centrifugal force outward, which is equal to, let's say if this is M and this is at a distance E, it is called M-E omega square, the centrifugal force. This force is always outward, which means radial. Its direction is always pointing outward. You know, a force has a magnitude and direction. The direction of centrifugal force is away from the center. And since the disk is rotating, and if you say, if you only limit the vibration in the vertical direction, so this is not going to move in the horizontal. Okay, you can put guide here, guide, so that it will only move in the vertical direction. So by rotating, due to the rotation, this mass, the eccentric mass that causing imbalance, will move 360 degrees. So when it reaches the horizontal part here, there is no force in the vertical direction. And when it reaches 90 degrees, it will give maximum force, because you can resolve this force into horizontal and vertical, okay, depending on the angle theta here. So if theta is 0, then the vertical component is 0, which is causing the excitation. If theta is 90 degrees, then the force is equal to ME omega squared, which is the maximum. And if it is 180 degrees, if theta is 180 degrees, then the vertical component is 0. And if the angle is 270 degrees, the force is equal to ME omega squared downward. So the force is applied with a frequency. What is theta equal to? Theta equal to omega times t. You know, that is theta equal to, in general, is omega 0 t plus half alpha t squared, right? If alpha is 0, then theta equal to omega 0 is constant, and it is omega t. Okay, for constant. You did this in dynamics. So this is omega, it becomes frequency. So the magnitude of the force is changing from 0 to maximum, to 0 again, to maximum, but in negative direction, and back to 0. And as this keep continuing rotating, this force is changing. So it is applied with a frequency, and it's causing force vibration to this, because you can have omega any value. Okay, omega can be any value possible. Okay, let's say this is 10 RPM, or it is 100 RPM, or it is 1000 RPM, or 3000 RPM, right? It can be any value, which is can be controlled. If this is driven by a motor, you can control the speed of the motor, and causes force vibration on the disc with by attaching a spring here. You are having a system that is excited by imbalance force. So this is one of the examples. There are many examples that can have force excitation. We will cover 3 types. Yes.
دكتور، الجرافيتي ما بيكون عليه تأثير حق الجسم إذا كان فعلى نقطة وأنزل نقطة؟
الجرافيتي؟
إيه دكتور.
اوكي. ده يعني دائما vibration is measured from equilibrium.
يعني neglected.
Yeah, it is not neglected, but the total you should consider. If you want the total deflection, you should consider the weight. But usually in vibration, we consider the 0 line is the equilibrium line, and then the vibration is the additional motion only.
تمام، يعطيك العافية دكتور.
الله يعافيك. Okay, so the frequency here is called excitation frequency, omega. Okay, so there is omega and there is omega n. Omega n is system parameter, function of the system parameters. Omega is any value, right? So what is the value of omega that is dangerous? There are 3 possible cases. Let me list it here. This has a natural frequency omega n. Okay, and excitation frequency becomes equal to omega. This is excitation. It is speed as well as excitation. So there are three possible values for omega. Omega is excitation frequency. And omega n is the nature frequency. So there are three possible cases. Either that omega is less than omega n, or omega equals to omega n, or omega greater than omega n. Right? There are no other cases. Either 1, 2, 3. One of them is most dangerous on the system. Okay, the dangerous means that, you know, the vibration amplitude, it is measured from equilibrium. One will cause maximum deflection. Which one you think?
Number 1 maybe.
Omega is less than omega n. Okay. Any other suggestions?
3 دكتور.
Okay, no. The most dangerous case is this. Okay, this is called resonance. This is called, the first one is called in phase. Okay, and this is called out of phase. Okay, what is the meaning of in phase? In phase, if omega is less than omega n, the frequency or omega n is, you know, this is to complete one cycle, right? Omega n is the reciprocal of time, 1 over tau. And omega in definition, in general, is related to tau. Okay, the time to complete one cycle. If omega is less than omega n, this will make a this will take more time to complete a cycle than if it is allowed to oscillate under natural frequency. Okay, so this is this is called in phase, which means it is slowly exerting a force on the system. That is, you can think of it as a response, or يعني خلينا نقول ردة الفعل. Okay, ردة الفعل. Response of the system under omega less than omega n is slow, so it will have low amplitude of vibration. And the same thing when omega is greater than omega n. Again, here omega, the time to complete one cycle is higher than when it is allowed to oscillate in natural frequency, and will have low amplitude as well. Here, when omega equal to omega n, by the time this is equal, they are equal. So by the time it is reaching maximum, you are giving it a push at the same time, in the same direction. It means you are making the amplitude even higher. And when it reaches the maximum, maximum, but in the negative direction, at the same time, you are giving a push to the system. So this makes the amplitude to be the maximum possible. Okay, that when omega equal to omega n, and it is called, referred to as resonance. You know, resonance means having the peak of the amplitude, reaching the peak of the amplitude, the maximum. So when it oscillates with omega less than omega n, amplitude will be something like that. Let's say this is A1. يعني amplitude 1. And when oscillate for out of phase, this will be even smaller, huh? Okay, let's call it A3. Okay, and when it oscillate with At resonance, this is going to be very high. Its amplitude is very high. Okay, that's what is called resonance. Resonance because amplitude is going to be the largest near or at resonance. Okay, so reaching the peak is called resonance. And in vibration, it means we have large amplitude. Now, for a spring mass system, let's see this system. Okay, the spring will be heavily loaded at resonance, not at in phase or out of phase. And what happens if the spring is under high loading or large amplitude? It will break. It is under fatigue, but when the displacement is very high, it means it will break quickly in that case. So the most dangerous case on a system when it is oscillating at omega equal to omega n or very close to omega n. Okay, which is called resonance. So equal to omega n or very close to omega n is very dangerous case. And there is no way to stop the vibration if you don't have a damper. So this is why there is some of the system they have dampers. They have viscous dampers to absorb the energy and reduce the amplitude or limit the amplitude to safe value at resonance. Okay, and we will talk about this phenomena in chapter 3 because chapter 3 is about force vibration. So the high amplitude or high frequency or omega is greater than omega n is not the dangerous case. And also the same thing for when omega is less than omega n, this is not the dangerous case. The most dangerous, they might be, it depends on the amplitude, by the way. And this can be dangerous if the amplitude is high. Okay, also this can be a dangerous case if amplitude is high. But the most dangerous is the number 2, is when it is at resonance. Any questions? Okay, so those are 2 main cases of categories or 2 categories of vibration. The force vibration takes place under the excitation of external force, which means you are forcing the system to oscillate with omega. And this omega is called excitation frequency and can have 3 different values. If the excitation frequency coincides equal with the initial frequency, omega n, resonance is encountered. And a dangerously large oscillation may result. Okay, they're saying may because if you have viscous damper, then you can limit the oscillations, the amplitude of the oscillation. But if you have no damper or you have minimum damping, this is going to cause large oscillations that will be dangerous and can cause breaking to the spring. Other categories are undamped and damped systems or vibrations. Definition of that is if no energy is lost or dissipated in friction or other resistance, okay, oscillations, the vibration is known as undamped. Otherwise, it is called damped vibration. So there is different ways of dissipating energy, either by friction, and friction in mechanical system is always there, and this minimized by putting lubrications. And sometimes you add a viscous damper on purpose. You want to absorb energy. Where is that application? The suspension of the cars. Suspension of the car is always to have the shock absorber consists of a spring and viscous damper. because it is you want to have a smooth ride as well as stable. Okay, without oscillations. Whenever you when you drive your car over rough road or over a hump. Okay, without the damper, this oscillation will be very high because the stiffness of the suspension is relatively soft compared with the weight, so that you can have a smooth ride in the car. Other uses of viscous damper in the punching machines. You know, punching machines by nature is impacting on work pieces to produce holes. So there is punching all the time, or cyclic punching, and that will cause excitation or free vibration that to be suppressed with viscous damper or isolators. Other types of categories is linear vibration, nonlinear vibration. So this the linear vibration is going to be the one that we will cover in this course. Okay, linear vibration. When the system is called linear is when the differential equation or equation of motion contains linear terms. Okay, so for the pendulum, is a nonlinear vibration. Why? Because the differential equation, I'm just going to give you the result. That is theta double dot plus G over L sine theta equal to 0 for free vibration. This equation is nonlinear because of the nonlinear term. Okay, this can be linearized as theta double dot plus G over L theta equal to 0. This is linearized. Why it is linearized? This is valid for theta very much smaller than 1 in radian. Okay, 1 in radian, not in degrees. So by nature, the pendulum is nonlinear vibration, but we will do approximation that sine theta is theta. Okay, for theta very much smaller than 1, sine theta is theta. You can do this for small oscillations. This is one way of saying nonlinear, is that when the differential equation has nonlinear term, or when the deflection is large or large oscillation. Okay, so linear vibration is characterized as linear differential equation and small oscillations. Okay, so we have linear differential equation and small oscillation. For nonlinear vibration is large oscillation and nonlinear differential equation. Okay, some nonlinear problems like the pendulum will be linearized to linear equation. This is called linear equation. This is nonlinear. Okay, so I'm going to stop here. Any questions? We will do lecture 2 next time. Okay, assalam.
دكتور.
نعم.
Yes. Clear.
Clear. Okay. Okay. Thank you.